Hello. Hello, and welcome to United Astronomy Clubs of New Jersey. So, first things first, we are actually in Jenny Jump State Park on our lovely observatory grounds. And because the weather is weathering, we do have a brief safety uh, for that.
Hello, everyone. I'm Paul, and I just want to remind everyone that a tent is not the place to be during a near miss or, if we were to get hit directly by a thunderstorm. So, rain we can handle, thunderstorm with any significant wind or thunder and lightning activity. We'd ask you to either join us inside in our museum or to go to your cars. You, of course, may choose to leave. We would try to restart if it's going to be a momentary delay, but it might turn into, based on the weather, might turn into a longer term delay. Either way, reminding you that a tent is not the place to be, so it asks you to get out of the tent and find better shelter to weather a thunderstorm. Thank you, everybody.
Yes, oddly enough, a structure composed mainly of metal poles, grounded into bolted into the ground, conducts electricity fairly well. Right. So with that, uh, back to our normal briefing. While I see some people filing down, do check us out on our website, uacnj.org. That's where you're going to find all about our organization, our upcoming presentations, and even our past presentations. And we do live stream this to YouTube and Twitch. So if you ever can't make it out here or are just looking for something to do on a Saturday night, uh, do join us in chat there and hit those like and subscribe buttons so we know that we're doing a good thing. Uh, Also, check us out on our social media: Facebook, Instagram, Twitter. That's where we post when we're going to go live, as well as any fun other events that we might be doing and events that our member clubs are doing. With that, I come to the usual safety briefing for everyone who has joined us here. If you need to use the bathroom, it is the porta potty to my uh, left, your right in the back by of the tent. I do have, like Paul mentioned, a little museum slash gift shop area that you can check out after the presentation. I'll be in there manning it at that point, unfortunately. Still haven't managed to get hold of that secret be in two places at once technology. Once they do that, I will take over the world. Not really. That sounds like too much effort. When we go to leave, chances are it's going to be dark. Use our headlights because we do not like getting run over, and I'm sure you also feel the same way that getting run over is not something we want to add to this rainy weather. If we're using flashlights to wander around, please keep them pointed at the ground though, because we don't, or if you happen to have lasers, again, keep them pointed towards the ground, or, well, lasers shouldn't be pointed towards the ground, but use them mindfully so we're not actually getting them in people's eyes. With that, our talk tonight is Unusual Objects in the Universe with Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. Walt is a member of the North Jersey Astronomical Group and the Rockland Astronomy Club, and he's been volunteering here at Jenny Jump for over 20 years. And with that, Walt.
Thank you. That really does make me sound old. I guess I am. Well, welcome everybody. Thanks for braving the storm and stuff and coming out to consider some unique objects, unusual objects, or even strange objects. I kept. Oh, pardon me. I kept vacillating on the name of this talk because there are some strange objects and there's some unusual objects as well, and there's some unusual strange objects. But you know, the better our technology, the more we find answers to some of our questions, but we find a lot more questions too. And we see that the universe, even in its normal stages, is a very strange place. And there's just all kinds of interactions going on that that are just hard to comprehend. I mean, we can talk about it in words, but to really comprehend what's going on in some of these objects and the power behind them is just amazing. And I hope I can share some of that with you. I do these talks really, I hope that I get someone interested enough to go out and just Google some of this stuff and get interested in astronomy. That's my hope in doing these talks. None of this stuff that I have tonight is proprietary. I got it all. All the pictures are off the internet. I have the attributions down in the left-hand corner. And so you can do the same kind of research, and I hope you do. So some of the technology has let us use different wavelengths to see the same object in different light. And I just want to spend a minute talking about wavelengths so you can kind of understand what I'm talking about. The electromagnetic spectrum goes all the way from radio waves, which can be like a kilometer long, all the way up to gamma rays, which are super tiny and full of a lot of energy. That's the electromagnetic spectrum. And we only see this little rainbow area here of visible light. Our eyes don't see infrared and beyond, and they don't see ultraviolet and beyond. But we have instrumentation that we put on telescopes that will allow us to see at those wavelengths. And when we make pictures, we can make pictures that show us in color what we see in those wavelengths, and we see detail that we could never see with our visible eyes. We can't see color, even in the visible spectrum. When Hubble was taking pictures in the visible spectrum, you could see beautiful colors in their images. And if we look at a telescope at those same images, we're not going to see those colors because our eyes are like a 1/30th of a second camera. And that's not enough to gather light. What you have to do is you have to have a big light bucket, a big opening, and you've got to take long exposures. Even the astronomers here, they'll take 1, 2, 3, 4 hours of photographs and stack them together to get the color that you see, even in amateur photographs. But the digital world has made that so much easier. When I started out, we did the film, and we'd have to take guided exposures for 45 minutes. And that was just a masochistic endeavor. That really hurt. Now you can just take 100 one-minute photos, use Photoshop, stack them up, and have a really nice looking photograph without worrying about tracking an object for a whole long time. So here's an example of what different wavelengths can do for us. This is the Eagle Nebula. Both were taken by the Hubble Space Telescope. On the left, we've got a photograph taken in visible light. And if I looked in a powerful telescope, I could see that, but it would just look cloud. It would be black and white image in my eye. But I could see that structure. And what you're looking at is a lot of dust clouds. This part of the Eagle Nebula is known as the pillars of creation because it's giving birth to stars constantly. What happens is the dust starts to collapse on itself, and the gravity increases, and it gets tighter and tighter, and it starts to heat up. And when it gets hot enough, it lights up under nuclear fusion, and a protostar blinks into existence. And then it changes size a little bit until the force of the fusion pushing the star outward and the gravity sucking it inward equalizes. That's called hydrostatic equilibrium, and then you have a stable star. Our star, the sun, has been in hydrostatic equilibrium for about 5 billion years, and we expect another 5 billion years. It's about a 10 billion lifespan. The hotter and bigger the star, the quicker it'll die. It'll go out. It'll stay less on what we call the main sequence. Over here is a Hubble telescope photo done in near infrared. Now you could see the infrared can cut through a lot of the dust. So we get a lot more information on the stars behind that we couldn't see. You see, this dust is obscuring stars that this is showing. Also, the background stars all through here are now coming into view. This trapezium's amazing. So both photos give us a lot of information, but they give us different types of information that we can use. On the left is the new James Webb Space Telescope. This was a picture taken in near infrared. Infrared that was a little closer to the visible spectrum than the Hubble Space Telescope that we just saw, which is right here. It's the same photo we just looked at. You can see there's more detail in the cloud, but there's still a lot of detail that we are getting through the dust. The James Webb scope is going to be mostly in near infrared, taking pictures in the near infrared. Okay, here's my first strange object, and it's in our neighborhood. Anyone have a guess what we're looking at here? Yeah, thank you. Exactly. This is the hexagon on Saturn. And the view is of Saturn's north pole down to about 70 degrees. And if you look, you can really see there's two hexagons, one within the other. And when this was discovered, people were just amazed. It was discovered on the Cassini mission. It's a bunch of cloud structures with numerous vortices here. And there's a massive hurricane tightly wrapped around the North Pole. This is a massive hurricane. The eye is about 50 times larger than the average hurricane eye on Earth. And the hexagon and that hurricane spin counterclockwise, while some of the vortices, which appear as red ovals, they spin clockwise. And the big white dot right here, that's the largest of the vortices. It's about 220 miles wide, and it's twice the size of the largest known hurricane on Earth. And when we see a picture of a hurricane on Earth, I mean, it takes up an appreciable part of the Earth when we see it how much it covers. Here, it's just a little piece due to Saturn's amazing size compared to Earth. Yeah.
Keep that in mind, everybody. I'm sorry, Walt.
Yep.
Go ahead.
No problem.
So it will be possible that we can continue inside after a brief pause if that does happen. It's just going to take us a few minutes. So online people, you're going to have to bear with us, and you guys will as well, as we move inside if we need to, okay?
Okay, here's a fun fact on thunderstorms. Light travels almost instantaneously when it's on Earth, and sound travels at 1,100 feet per second. Okay, this is like the poltergeist thunderstorm here. Okay, am I talking inside or am I just bringing my computer in? Okay.
All right. So people online, just hold on a minute while we move inside. Public, if you could just kind of chill in the museum area while we move our presenter to where he needs to be. Otherwise, he won't be able to get through.
thunderstorms. Thanks. Light moves almost instantaneously. Sound moves at 1100 feet per second. So if you count the time between the lightning flash and the thunder, you can tell how far away the storm is. If it's 5 seconds, it's a mile away. If the next time is 4 seconds, then it's closer, right? If it's further, then it's further. So you can estimate how far away that thunderstorm is just by counting the time between the sound and the light. But we have left the Earth already, so let's go back to Saturn. As I said, oh, that's good. Okay, where this smudge is pointing to is the largest vortex that we were talking about. It's 2,200 miles, which is twice the size of the largest known hurricane on Earth. Andrew Ingersoll, a member of the Cassini team, noted that the hexagon is just a current of air, and weather features out there, meaning outside our door, that share similarities to this are notoriously turbulent and unstable. A hurricane on Earth typically lasts a week, but this has been here for decades, and who knows, maybe even centuries. Amazing. You'd think, you know, the Pentagon was discovered in 2006, and given the planet's high winds, sometimes going up to 300 miles per hour, you'd think that this would be unstable and would break up in no time. But what they did is after this was discovered, they went back and they looked at the film from the Voyager in the 70s. And they saw it in those pictures. They didn't have as clear-cut a picture as this, but they could see from those pictures that, yeah, this Pentagon has been here at least through the 70s, and who knows, as he said, it could have been centuries. We won't know. This must be turned off. Yeah, okay. There we go. All right, so we've got a lot of weird stuff right here in our own solar system, and Jupiter's largest moon, Jupiter's closest large moon is Io. It's near the top of my list of weird stuff in our solar system. Here's an ESA, European Space Administration animation of Io. And it shows a simplified view of the magnetic environment caused by Jupiter and Io. Io releases about a ton of sulfur dioxide every second due to all the volcanic activity on the planet. And the sulfur dioxide becomes ionized and trapped, and you see this toroid. It's like a donut around Jupiter. It's a rotating magnetic field, and it's generating an ionized plasma torus around the planet, just from the sulfur dioxide that's being thrown off by Io. But that's only part of Io's uniqueness. Here's a picture of Io. And I mentioned the yellow torus that was formed by its volcanic activity. Well, Io is the most volcanically active body in the solar system, with 100 plus active volcanoes. There's at least half a dozen volcanoes erupting at any given time on the surface of Io. So the face of the moon is constantly changing. It's been nicknamed the pizza moon. The colors you see are a result from the sulfur from the volcanoes in various stages of solidification. And that's still not all. Io, which is about the size of our moon and is about the same distance from Earth as our moon is, it changes its position visibly. If you're looking at it from Earth, it changes its position visibly in an hour or so. Io orbits at the same distance that the moon orbits the Earth, and as I said, they're similar in size. But while the moon takes 4 weeks to go around Earth, Io takes just 42 hours to go around Jupiter, which is, and Jupiter is a whole lot bigger. It's 318 times as massive as Earth. It's 11 times wider than Earth. And Io is going around this thing in less than 2 days to our moon's 4 weeks around a much smaller planet. It's just amazing. It's really Jupiter's mass that's just whipping it around at 38,700 miles per hour, compared to Moon's 2,288 miles per hour. If Earth were the size of a nickel, Jupiter would be the size of a basketball, just to give you a kind of comparison for the size there. And Jupiter can fit almost 1,000 Earths inside. So, you know, a lot of this instability has to do with tidal forces as well. Like the moon causes our tides. Well, a tidal force here is, if this was Jupiter here, the gravity on this side of Io would be a whole lot more than the gravity here, because it's close and because Jupiter is so massive. So tidal forces plays a good amount, plus, as I said, that magnetic field. All right, on to another strange object. Anybody know what this one is? Excellent. Yeah. Dr. Robert Work spotted Oumuamua October 19th, 2017. And I'm really impressed that you could say that off the top of your head. I always have to read it. I have been to Hawaii, but that's one that, I don't know, it just gets me. He was using the Pan-STARRS telescope on Mount Haleakala on the island of Maui, and I got to see that just 2 months ago. Really cool setup. The object was named Oumuamua, which in Hawaiian means scout, or one who arrives first. That's a really creepy name. I mean, think about it. You have an unknown object, and you name it the one who arrives first. Oh boy. The object was described as a cigar-shaped, reddish in color. This is an artist's conception of it. We don't have a picture. We just saw it as a blip, and it's gone already. It's about 1 kilometer long, which makes it kind of small. Only 167 meters or less wide. It was traveling so fast that it was definitely not gravitationally bound to our sun. At first we thought it was an asteroid. And you know, asteroids and comets travel in the solar system around the sun in an elliptical orbit, right? So they'll come around the sun, zip around, and then sometimes they'll go way out, thousands of years, and then come around. And so sometimes the ellipses are not that elongated, sometimes they're very elongated. Oumuamua was traveling in a parabolic. It was definitely outside of our solar system. And so a parabola is you come in from outside the solar system, you hit the sun, you whip out, and you go out in another direction. But you don't make that ellipse. You come into the solar system and out. We figure it probably entered our solar system about 150 years ago. In August 2018, there was a study done using data from the European Space Agency's Gaia telescope, and they identified 4 stars that Oumuamua probably would have passed close to in the last 1 to 7 million years. And they think perhaps one of these was the home star that it came from. Here's another rendition, and there's a bunch of theories for Oumuamua, obviously. An early theory was that it was an asteroid, but scientists discovered that the sun's gravity was not the only thing propelling it through space. This led researchers, including a Harvard University professor, to speculate that it was some sort of space probe, which has been pretty much debunked. It's not one of the big hypotheses. The current consensus is really that it's some kind of comet, and that the comet had hydrogen frozen in the ice, and when the ice melted, the hydrogens formed little jets, which I guess this artist is trying to show, that caused the additional increase in velocity. Of course, there was no tail that you would expect in a comet, and it's more than twice reflective as your average comet, but it's still a plausible explanation. We do know of what they call dark comets. They're unusual, but they exist. In any event, it was visible for a time, and now our chance to observe it is past because it's back outside of our solar system. So that's kind of an interesting. We don't get many of those visitors. Of course, as our technology improves, we may find out that there's more chunks of rock coming from outside, similar to this than we even realized. But while we're on the subject of alien structures, and I'm doing this, I'm saying this tongue in cheek. Please don't think I'm one of those Area 51 guys, but you don't rule anything out, because that would be ignorant as well. But this is a star, a very unusual star called Tabby's star. It's an F-type main sequence star with a red dwarf companion in the constellation Cygnus, which is about 1,400 light years from Earth. So if we had clear skies, you could look up and see the constellation Lyra and Vega, a very bright star, which you see right here. And even if you couldn't see Tabby's star, you would see the Northern Cross and Cygnus and the area that Tabby's star is from. The fact that it's an F-type main sequence star means that it's a little hotter than our sun, and red dwarf companion means that it's a binary star system. So there's another star and with Tabby that's gravitationally locked with it. The star is named after an American astronomer, Tabitha Boyajian, who was a lead author of a 2015 paper that announced the discovery of the star's irregular light fluctuations and just the how it acts a lot differently than variable stars, than many variable stars. There are lots of variable stars out there. There's the AAVSO, is an organization that just monitors variable stars and collects data, and amateur astronomers collect that data. So here are two pictures of Tabby's star. One's taken by infrared on the left, and the other ultraviolet. So what? It's not that impressive. It looks kind of boring. The real difference comes in how it dims over time. Most variable stars have at least predictable periods where an object like a planet or a companion star passes between the star being observed and Earth. So you'll get a planet pass through, or you see if there's a red dwarf, the red dwarf would pass in front of the star, and that would have a periodicity to it. We could kind of predict when it was going to dim and when it was going to get brighter. But Tabby's was just all over the place. Only Tabby and a handful of others stick out for the difficulty of figuring out why they dim. If you Google variable stars, you'll get like 50 different types of variable stars. Some are the star itself is pulsating, and other times, as I said, it's an object that's passing in front of it that we can know with pretty regular prediction when it's going to get dim. But Tabby's star dims irregularly, dropping by as much as 22% for several days at a time. And with other variable stars, the most likely explanations is that something's passing in front of the star. But these brightness dips were too significant to be caused by an orbiting planet, so scientists began suggesting alternative explanations. And for a while, a popular hypothesis was that it was a gigantic energy-collecting structure built by intelligent civilization, such as this. But researchers have been keen to stress that this alien megastructure scenario is quite unlikely. And I'm sure you'll find plenty of people on YouTube that'll take this way out there. Tabby herself, Tabitha Boyajian, has spent years studying this star named after herself. And she's detected that some forms of energy will shine through during the dips, which would preclude solid panels, such as the one would expect to see in a Dyson sphere. And this is an artist's conception of what a Dyson sphere. See, these solid bands would not let any light through. And what Tabitha is saying is that some wavelengths are coming through. So she doesn't think it's going to be a solid structure like that. She's precluded that. More likely, swarms of objects similar to a family of comets or remnants of a smashed moon or planet or an asteroid belt is probably the cause. Possibly a deep space object that's between Tabby's star and us that has nothing to do with either system. This is just an alternate guess by an artist depicting what he thinks Tabby's star would look like. You see the comets and you see a dust band. So you're seeing stuff that is kind of translucent where some light will get through, but is enough to dim the light from a star as we observe it. And so that's the most popular explanation. But only time will tell. We're still figuring that one out, just like most of the stuff that I'm going to present here today. There's a similar object, and it's in a catalog called the Exotica catalog. And the name of the star is VVV WIT 07. Sounds very scientific. Just a spoiler alert. The WIT stands for what is this? And you will see in some star catalogs, you'll see a star with that an object with that designation, and there's wondering, what is this? So scientists don't know everything. This star is near the center of the Milky Way galaxy in the constellation Scorpius. It's located more than 25,000 light years away from Earth. It was observed in a deep eclipse. Around an 80% dip in its light was observed. And that was in July of 2012. Scientists aren't sure if it's another Tabby star or a MAMAJEX object. What's a MAMAJEX object? I had to ask myself that because I hadn't heard of it till I started looking into this object. This is the MAMAJEX object. This is where Eric MAMAJEX from the University of Rochester, this was the object that bears his name. It's a huge ring around a planet that eclipses a young sun-like star. In this case, it's a brown dwarf much larger than Saturn with rings eclipsing the star JI 407. Right? So this is a brown dwarf object, and these rings are huge. They eclipse the star. And the reason why is because there's at least 30 rings around this planet, each of them tens of millions of kilometers in diameter. Huge. And they also found some gaps in these rings, indicating that exomoons may have formed as well. When you hear the term exomoon or exoplanet, all that means is it's a planet or it's a moon outside of our solar system. So an exomoon is just a moon that's in another system other than ours. If we replace Saturn's ring with these rings here, they would easily be visible at night from Earth and many times larger than the full moon. So it wouldn't be as bright as the full moon, but they would be the span of a couple of full moons, and we'd be able to see them at night. So it's just, like I said, incomprehensible, some of the things that are out there. So that's a MAMAJEX object, and it may be responsible for the VVV, what is it, 07. Let's switch gears. My next strange object is known as a Fermi bubble. This is a pretty interesting stuff. It's only known for about 13 years or so. In 2010, observations using the Fermi Gamma Ray Space Telescope revealed previously unknown features in our own galaxy. They're now known as Fermi bubbles, and they are these magenta-covered bubbles that we see here. We're looking at a composite of X-ray, gamma ray, and visible light. I didn't see exposure information on this, but this is definitely a visible light. This is our Milky Way galaxy edge on, and there's our sun. Each of these bubbles is 25,000 miles high. I'm sorry, 25,000 light years. Big difference. 25,000 light years up and down, and they're almost like a mirror image. Our Milky Way is 100,000 light years across. So we're talking about half the length of our Milky Way here in the height of these two bubbles put together. The photo, let's take another look at these. This definitely doesn't have visible light in it. Again, I couldn't get information on what kind of data they were compositing in these two pictures. They were on NASA's site. They're usually better than that. But this is probably all Fermi gamma ray data. You can still see the bubbles very clearly, and this is a higher level of radiation than the rest of our galactic disk, which again we're seeing edge on. We know that black holes ingest a whole lot of matter, large amounts of matter, sometimes stars, and sometimes they produce bipolar jets. Sometimes they're called relativistic jets. And then they shoot out from both ends of the black hole. So astrophysicists hypothesized that these Fermi bubbles are the remnants of such activity in our black hole at the center of our galaxy. The Fermi bubbles produce higher energy gamma rays than the rest of the galactic disk, and you can see, again, the difference in the intensity. Now, just to give you an example of a bipolar, this is an artist's conception here of a bipolar disk, sometimes known as a relativistic jet. It's a black hole devouring a nearby star and releasing huge amounts of energy. They're often called relativistic jets because the matter is being ejected at close to the speed of light. These things are just, I can't even imagine something like that. This doesn't count as one of my strange objects because these things are found throughout the universe. They're not all that particular. We may not have all of the physics down, but they're not that unusual to see relativistic jets coming out of black holes. And on July 29th, I'm going to be speaking on black holes a little more when I talk about the death of stars. If you want to come back, maybe we'll even have better skies. So in order to talk about my next weird subject, my next weird object, let me give you a quick lesson in galaxies. It's a bit oversimplified, but there's three general types of galaxies. There's the elliptical, spiral, and irregular. You know, and then you get the barred spiral is still a spiral, and you get a whole bunch of subcategories, and you can categorize these till you're crazy. But those are basically the three basic types, and a couple of examples of the shapes you see. So take a look at this. Astronomer Arthur Hogue found this unusual object in 1950. On the outside, we see a ring of very blue stars, which doesn't show up too well as blue, but they're very blue stars, indicating they're young and they're hot stars. And there's a center of redder stars in a ball in the middle. And between the two is darkness, for the most part. We don't know how this object formed. We're still guessing at it 70 years later. Even the circularity of this object is very unusual, and it may have something to do with their formation, although we still don't really have a good idea on that. The object is 100,000 light years across, and we just heard that number before because that's how wide our Milky Way is. So it's about as wide as our Milky Way. It lies about 600 million light years away from us in the constellation Serpens. And this is called a Hogue, H-O-A-G object, after Arthur Hogue, the person who discovered it in 1950. And coincidentally, this is another ring galaxy further back that we just happened to see through the space there. So what are the theories about this? There certainly are theories. One of the early theories was that we were looking at a gravitational lensing effect. Now, gravitational lensing effect is when there's a massive object, if there's a very massive cluster of galaxies here, they actually bend space-time, and we see this. And so there could be a galaxy behind it that the light is actually bent around so that we could see it where we wouldn't normally be able to see it behind another galaxy. And that's exactly what we're looking at in this. This has nothing to do with Hogue. I'm giving you an example of what gravitational lensing. The position of this mass is almost given us a perfect circle. A lot of times you'll see arcs like this and maybe an arc out here. You'll see all kinds of arcs around very massive galaxies when we take pictures with the Hubble. So they were saying, well, look, this is yellow and this is blue. Maybe that's what it is. Well, one of the ways we tell the distance of objects is by the redshift. The universe is expanding, and the farther away an object is, the faster it is moving away from us. And when it moves away from us, its spectrum of the elements that are in it gets shifted to the red. Just like when you hear a train coming at you, the pitch gets higher, and then as it goes away, you hear the pitch go lower because the sound waves are being stretched out. Well, it's the same thing with light waves. These things are moving so fast away from each other that the red is shifted. And so if you have two objects like this is about 5 billion light years from us. This is 10 billion. They have very different redshifts. You can tell that these two objects are not connected. They're 5 billion light years apart just by measuring their redshift. And so when we look at Hogue, we see that the two elements we see this element, the circle, and the ring, they both have the same redshift. They are both in the same neighborhood, not like a gravitationally lensed galaxy. So another hypothesis is that it's two galaxies collided billions of years ago, and the gravitational effect of a central bar has since vanished. We've discovered a large number of objects that look very similar to a Hogue's object since its discovery. They usually involved a large and a small galaxy colliding, as we see in this. This is the Cartwheel galaxy. And so we see one galaxy collides with another, and the high-speed collision forces matter outward. That compresses the gas and forms new stars. And so you see a blue ring of new hot stars that were formed by the shock wave of this collision. The gases compress, the dust clouds compress, they get hot enough to ignite, and then we form new protostars, and they show up in bright blue color. NASA's website states that observations in radio waves indicate that Hogue's object has not accreted a smaller galaxy in the past billion years. An article in Forbes magazine, of all places, on this subject pointed out that this type of ring galaxy has certain features that are lacking in our strange object. The identification of a second galaxy with a distinct population of stars from the main galaxy. We see that here. We don't see that in the Hogue's object. The presence of faint fragments of a collision that should persist for billions of years. We don't see that in the Hogue's object. And a high relative velocity between multiple components of the system. So what they're saying is that the relative velocity between these components, there's a big difference there. We don't see that in the Hogue's object. It indicates a much less violent formation process. So it's been 70 years, and we still just have to be humble and admit we haven't figured that one out yet. But that's a strange one. Let's take a quick look at the science behind the life cycle of a star. And I'll be doing a whole hour on this later on in the summer. I'm just going to give you a very, very oversimplified version of it. an average star like our sun, up to about 8 solar masses, when it runs out of hydrogen, eventually it'll turn into a red giant. The gravity will not be strong enough for it to hold its outer shell, and about half of its mass will come out as a planetary nebula, usually very beautiful, and leave a white dwarf star behind. If it's a larger mass star, over about 8 solar masses, about eight times the size of the sun or more, it'll become a red supergiant. And the nuclear reactions will eat up more and more elements until it gets to iron. When it gets to iron, you have a cataclysmic explosion known as a supernova. And up to about 80 masses of the sun, you'll end up with a neutron star. Over 80 solar masses, you're probably going to be left with a black hole. So that's just a quick look. What we're interested in is the neutron star. We're going to take a look at that. So that's somewhere around 8 solar masses to 80 solar masses. Those are very general numbers. There are all kinds of different nuances and different flavors of these explosions. But we're going to look at this neutron star. So here's a Hubble photo of my favorite neutron star supernova remnant. It's called the Crab Nebula, also known as M1. Messier made a catalog that astronomers use for some of the best views, best objects to view. Messier created it as kind of a garbage catalog. He was looking for comets, and there were these objects that looked fuzzy like a comet, and he kept running into them and realized, I should just make a catalog of all these fuzzy objects that I'm getting waylaid by, so I know where they are and I don't waste my time on them. And so M1 was the first one that he came upon in his catalog. This is a mosaic image from the Hubble telescope. At the time, it was one of the largest taken. It's 6 light years wide, and it's an expanding remnant of supernova explosion. What I think is really cool about this one is that Japanese and Chinese astronomers here on Earth recorded seeing this supernova go off in the year 1054. And it was so bright they could see it in the daytime for a while. And so when I look at this thing, it is so cool to think that there were people on Earth 1,000 years before me who actually saw this thing blow up, and now I'm looking at what it looks like 1,000 years after they recorded it. So cool. The orange filaments are the tattered remains of the star, and they consist mostly of hydrogen. There's a rapidly spinning neutron star left behind, just like our sun will leave behind a white dwarf. This explosion is going to leave behind this rapidly spinning neutron star at the center of the nebula. And it's powering this eerie glow. This little tiny star is powering the glow. The blue light just comes from these electrons whirling at nearly the speed of light around the magnetic field lines from this neutron star. And the neutron star, like a lighthouse, ejects twin beams of radiation that appear to pulse 30 times a second. Now think back to those relativistic jets I was talking about, how the gamma rays are just spewing out on both sides. That's what's going on here. You have a neutron star, it's putting out jets and it's spinning around. So when you're in a fixed location on Earth and you get to see one that's actually pointed towards you, you see it pulse. What's happening is it's spinning around and you're seeing 30 times a second, you're getting an energy burst that's coming from this relativistic jet of the pulsar. So 30 times a second, a neutron star is an ultra dense crushed star. Some neutron stars can spin at 43,000 full rotations a minute, if you can picture that. They're about 12 miles or so. The average neutron star is about 12 miles. It's like the island of Manhattan, spinning around thousands of times a second and throwing off energy like a lighthouse, throwing gamma rays out. So these stars are also known as pulsars because they seem to pulse, just like a lighthouse. A neutron star can have a mass greater than our sun, but be only 12 miles across, as I've said. So usually it's half of the masses of the stars lost here, and then it's got half the mass there. So imagine just our sun, which is smaller than this original star. It's 333,000 times more massive. It weighs more than the Earth. Imagine the mass of 166,000 Earths packed into space the size of Manhattan. That's 166,000 Earths packed into the space of Manhattan. That's what you're looking at in a small neutron star. We're talking about a tiny star that's approximately 1 trillion times more dense than our sun. And pulsars are not uncommon, but they are definitely strange. Hurts my brain to think about them anyway. So here's a little connection with a neutron star. Maybe, because we're not entirely sure what causes fast radio bursts, which I'll call FRBs. It's a phenomenon that still has scientists scratching their head, and quite frankly, there may be a number of explanations for what causes these. There may be a number of causes because there's a number of different flavors of these fast radio bursts. There's sudden rapid chirps in the radio wave spectrum that often only last a few milliseconds. Most appear to come from outside the Milky Way, even hundreds of million years away. Hypotheses include colliding black holes and extraterrestrial civilizations. That's like one of their throwaways, you know, and it could be extraterrestrial civilization. It's not a serious contender for the theory. Today we're a lot closer to understanding these FRBs, but we're still far away. New discoveries have led to new questions. There's a very active area of discussion in astrophysics on what causes these and if there are a bunch of different causes. A Scientific American article from November 2021 was very helpful to me in explaining this phenomenon and where we stand with the research. The combination of new detections and deeper studies have led to a narrowing down of the possibilities for the origins of FRBs. But it also has led us to understand that it's probably not just one explanation. We now know that these explosions, some of which produce as much energy as in a few thousandths of a second as our sun does in a month. I'll say that again. Some of these millisecond explosions produce as much energy in a few thousandths of a second than our sun does in an entire month. Happens about 800 times a day, and they're scattered all over the sky. So they're happening all over the place. We've observed this. And now we know that the bright light that accompanies these explosions can reveal much about the deep space it crossed to get to us. So in other words, if we capture data about that explosion, these are often highly polarized. And the way that they arrive to us tells us about what kind of materials they've interacted on their journey to our observing station. So they're thinking this may be helpful in mapping some of our universe. That's where they think the scientists think the technologies are going. So in April of 2020, 3 separate teams of observers detected an FRB originating from a magnetar. And that was located in our Milky Way. It was a real, I won't say stroke of luck because 3 people observed it. So they were looking hard and they all found this. They knew that there was a magnetar there, and a magnetar is an extreme neutron star. If you thought a neutron star was extreme, add to it a ridiculously strong magnetic field. Adam Mann notes, he's the author of this article that I read, Adam Mann notes that the magnetic field of a magnetar is so powerful that approaching it within 1,000 kilometers would disrupt your body's nuclei and electrons, causing you to effectively dissolve just from the magnetic field. Inconceivable. Magnetars were already a candidate for the cause of FRBs, but none were directly observed coming from one until April of 2020. This discovery inside our galaxy was just what the scientists need. This is just another artistic impression of FRBs. One artistic impression is as good as another here, because we really, how do you possibly kind of illustrate this concept? Some scientists saw an X-ray flash following a radio signal, suggesting that there's a complex process, even more complex than they thought. We still need more research on the how the magnetar produced the FRB. Was it from inside the star? Was it a star quake? Was it in its magnetosphere? Or in the material around the magnetar? Stay tuned, because we don't know. And of course, one observation doesn't carry the day. We already know that there are FRBs, that the FRBs can be one-off events, or they can be multiple events. FRB 121102 was observed in August of 2017 to give off 93 explosions just in one day, ruling out a single event as a cause. And of course, there may be two separate causes for repeating and non-repeating FRBs. There's a lot more non-repeating FRBs than there are repeating FRBs. Sam Chatterjee, an astronomer at Cornell University, notes that magnetars can explain some fraction of FRBs. Nobody would dispute that, but is that all of them? Almost certainly not. And I think since Shami spoke, we've come up with evidence that magnetars certainly can't be the cause for all of them, because we observed we observed an FRB in a globular cluster. A globular cluster are clusters that surround galaxies. We have about 110 of them, 112 of them. And they have stars that are very old, about 10 billion years old. And they observed an FRB coming from one of these globular clusters. A magnetar is very unstable, and in about 10,000 years, it settles down to just being your plain run-of-the-mill neutron star. So a magnetar is, you're not going to find a magnetar that's been around for even 1 billion years, let alone 10 billion years. So the discovery of this FRB coming out of a globular cluster has pretty much said, hey, we've got at least 2 different causes of these FRBs, and obviously maybe a whole lot more. Maybe they're the product of many different reactions that we're just starting to learn about. But as I said before, the ultimate goal of scientists is to try to map matter throughout the universe using these FRBs, using the information that comes through their polarization and their changes in polarity as they make the journey here. I'm going to just skip this one. And I'll spend a few minutes. I guess I'll go, should I go a little longer because we took a break, or when do you want me to, 5 minutes? All right. I'll go about 5 minutes, and then I'll open up for questions. Let's just take a little look at this path here, black holes, because they're rather interesting as well. This is a rendition of a black hole. Again, around 80 solar masses plus, we start to get a black hole. And although we can't see black holes, we can see their effect. We can see, because they're so massive, that they bend the fabric of time and space. And so we can see these gravitational lenses. We can see stars whose light travel past the black holes. We can see the accretion disk around the black hole as it gobbles up the stars. If our sun was a black hole, as dense as a black hole, it would be about 6 kilometers in diameter, so about a third of New York City. And mind you, the sun is 1.4 million kilometers right now. So we can't really see a black hole because light doesn't leave it, but this was the first direct evidence we had of a black hole. This came from the heart of M87, an elliptical galaxy in the Virgo cluster, about 55 million light years away. And over the course of 4 nights in April of 2017, we got enough data that we could compile this photo of the accretion disk. So this is a black hole. We're seeing its appetite for matter getting real hot before it spins into the black hole, and then we can't see it anymore. So this is as close to a photograph of a black hole as we've ever had. It's amazing. So here's some elongated objects I spoke about before with gravitational lensing. This is a giant lensed galaxy arc. The galaxy we're looking at is about 10 billion light years away, which is about a third the age of the galaxy. And it's been warped into a nearly 90-degree arc of light by the gravity in the galaxy cluster. The galaxy cluster is 5 billion light years away. So like the other photo I showed you, the galaxy with doing the gravitational lensing is 5 billion light years away. And we can tell by the redshift that the galaxy that has come out from behind, this galaxy that's all bent out of shape, literally, is really located right behind there. And it's the bend of space-time fabric that has brought its image out here for us to see. The coolest gravitational lensing, in my opinion, and there's some really great stuff out there, is an Einstein cross. This is gravitational lensing by a humongous cluster of galaxies here. And behind it, a supernova went off in one of the galaxies. And the light from that supernova was bent in 4 different directions. So what we're seeing is 4 slightly different stages of the same supernova through gravitational lensing. And Einstein predicted this years ago, but we actually got it on film. It's just amazing. Gravitational lensing always creates distorted and highly magnified images of what's behind it. So this is another strange, unique object. I'll just get through a couple other images. I kind of like this guy. This guy's called Gravity's Grin. Distant gravity. You know, we've got some galaxies there, and the X-ray radiation from those interacting galaxies is giving us a nice purple glow. It was taken from both Chandra and Hubble telescopes. It's also nicknamed the Cheshire Cat Group for some reason, I don't know. Again, these arcs are from gravitational lensing of galaxies behind that massive. And there's one more. If you got to merge, you might as well make it into a cool merger. These piercing eyes of this semi-creepy face are bright cores of 2 distant galaxies in the middle of a head-on collision. And they're surrounded by a mishmash of stars from their respective galactic disks. A ring of young blue stars. Whenever you have galaxies colliding, we always see young blue stars being formed because of the shock waves compressing the gases and forming new stars. Let me see if I wrote that down.
I'm sure online chat can also tell us
Yeah,
at some point.
Oh, the galaxy merger is known as ARP Madore, M-A-D-O-R-E, 2026-424. They love those handles. So this was captured on 2019. And it's my farewell face. I hope you found a few of these objects interesting. Gravitational lensing is just an amazing field. When we first had Hubble, we used to point to where we thought there was nothing and we were amazed at all the number of galaxies that we saw. There's a one deep sky photo of 1,500 galaxies pointed towards Ursa Major, where we thought there was nothing. But then they started pointing the telescope at really populated areas, and that's when they started seeing all this gravitational lensing, because they were looking at super massive groups of galaxies that were bending the light behind them, and that whole field has just opened up. So thanks for visiting tonight, braving the rain, and I hope you get a little observing in. I haven't looked, but I don't hear thunder. Any questions?
Right. So before we open it up to question and answer, there are a number of questions online. So we'll get into those. Once again, safety briefing. When we leave, we are using our lights. We don't like getting run over, and I'm sure you agree. Bathroom is the porta potty outside, and I'll be in the gift shop afterwards. I think it's still raining, so I don't necessarily think we have scopes open. But you're more than if you want, you can go check out views off the rock and whatnot, assuming it is safe to do so. It sounded like it. I do believe the storm has passed us. So how question and answer is going to work? For the people here, you're going to raise your hand. I'm going to pass you the mic, and you're going to speak your question into the mic, because chances are, if you have a question, someone else was also thinking the same thing and might not have been brave enough to actually ask it. So I'm going to open it up with the first online question I got. Why is the hexagon on Saturn shaped like a hexagon instead of a sphere or circle?
Good question. Everyone was shocked when they saw it, and they don't understand the physics behind the formation of such a perfect hexagon.
All right. Question. Perfect.
Hi.
Hi.
With black holes being all-consuming, how is it radiation can escape but light or nothing else can?
Well, radiation really it can't escape. I mean, there's something called Hawking's radiation, which is a very slow process of evaporation on a black hole. So it slowly leaks some of the matter, but there's no real radiation like a star. I mean, what you see is you're seeing the event horizon is when it enters the black hole, and then light's not escaping. So just outside that event horizon, when it's eating up large quantities of mass, that mass gets heated up as it's coming in, and it glows orange and red. It glows very bright, and there's a lot of radiation that escapes there. But once it falls into the black hole, that's it.
Right. So the next online question is, how did we figure out the shape of it? This was about I'm gonna butcher the pronunciation. Oumuamua. Yeah. How did we figure out that it was a cigar shape versus like?
They did get observations of it when it came close to us, and so we got enough observations to figure out the shape of it. But we didn't see it close enough to see, does it really act like a comet or how it acts? And we just saw it come in and out.
Right. Another question from here.
Thank you for the presentation. It was amazing.
Oh, thanks.
I'm just wondering, how do astronomers measure the energy concentration of stars?
Oh, that's a great question. Usually by the size and the spectrum. What chemicals they detect in the spectrum. That'll give it an idea of the class of stars, which tells you how hot it is approximately, and also the size of the stars. There's a HR diagram is a famous diagram. I'll show it when I do my life and death of stars talk, but it classifies stars by their luminosity and by their color, and that gives you a good idea of the characteristics. It also gives you an idea of whether they're going to explode in a supernova or not, because the larger stars are going to keep burning past carbon till they get to iron, where the smaller stars like the sun will just blow off their shell and they won't explode. But when it goes down to iron, once it hits iron, iron is the first nuclear reaction that requires energy instead of giving off energy. And so as soon as iron's formed, you have a cataclysmic implosion that just goes boom like that into an explosion that can outshine the billions of stars in a galaxy for a little while. It's amazing science.
All right. So I wanted to actually share this comment with from the online chat where Io kind of looks like a melon someone forgot in the back of the fridge for a while. But the
Io.
next online question was, how many space-based telescopes are there?
Oh my goodness. Hubble, JW, Fermi. You know, I'd have to guess at 8 or 10, but I'm not sure.
I don't know
I'd have to
either.
Google
So
that one.
maybe
I'm not great at lists.
I know Dan's watching. Maybe Dan can get on his wonderful internet box and tell us how many space-based telescopes there are. Next question. Perfect.
Another question. Do you know like any details related to like gas extractivism from like ash?
Space mining?
Yeah, through space mining, and basically like gases that have been retained from either asteroids or stars, planets, anything of that sort.
I don't know anything about that.
Oh, okay.
You're talking about sending people to mine it?
Well, I'm just wondering about like space mining and how, you know, basically gases or minerals or elements are obtained, and if you know details about
Well,
that.
you know, supernova explosions
Yeah.
are a big way that we get our elements, right?
Yeah.
Because the heavy elements are formed there, and when they explode, that's how they're formed. But to speak of space mining as if it's happening now, I'm not. I mean, we haven't sent people up to mine. We've grabbed a few moon rocks, but and there's plenty of resources out there. There's this one. Was it a planet or moon that is like a solid, super rich with gems, and you know, they put a price tag of trillions and trillions of dollars worth that you know we'll probably never get to. But yeah, as far as it happening, it's not happening yet. I think when there's something of value, humans find a way to get at it. But you know, the distances that we're talking about are just so amazing that you know, we have to find a way to put people in stasis and find people who are willing to dedicate their lives to doing it, because you know, space travel, even between the closest star to us is 4 light years away. That means if you travel at the speed of light, which we haven't figured out how to do, it would take us 4 years to get there. And so when you look for you look at something that you look for a star with some planets that might interest us, they're so far away. It's great in science fiction books, but it's going to be quite a while before we figure that one out.
Yeah. Dan was kind enough to supply a couple answers where we actually don't know the shape of Oumuamua, because there's 2 options based on the observation. Is that one, it's long and thin and tumbling, but the other is that it is possibly more spherical than we think. There are lots of space-based telescopes, but and he says you're probably thinking of the asteroid Psyche, which we currently believe is likely the core of a protoplanet. I don't know
Oh,
what
you
a
mean that mineral-rich
Yeah.
planet? Yeah. Okay.
All right.
Great.
I-
It's good to have someone on Google for me. Excellent.
Yeah, unfortunately, if I exit the online chat, I lose online chat and all the
Yeah.
questions stored. So I have to have someone else use their magical internet
Yeah.
box.
And it's amazing how quickly Google will answer questions. You know, I just something like, how big is Jupiter compared to Earth? You know, boom, it's right there. Yeah.
All right. Let's get your question.
I have many questions, but just quick one. What is space quakes? What are they?
A starquake.
No, it's starquakes. Yes.
Yeah, it's like an earthquake on the star that releases a high amount of energy.
All right. So our next online question had to do with the spectrum that visible light is on. You know, we have microwave, gamma, visible, ultraviolet, IR. They're all out of order. I realize that. So, you know, other things on that spectrum are kind of dangerous to human life, like X-rays
Gamma rays.
and whatnot. Is there possible? Is there an organism that might not be harmed by that kind of radiation that's harmful to us, but would be harmed by visible light instead?
Good question. As far as not harmed by the others, I always think a cockroach. I think cockroaches can just about withstand any kind of radiation.
Those and
But,
Twinkies will outlive us all.
What organism can be destroyed? That's a good one. I'm not big on biology.
I'm sure there's like a Star Trek or Star Wars episode with something.
Yeah, but we're talking about real life here, right?
Probably. All right. Another question?
For Oumuamua, just correct me if I'm wrong, but did you mention that historically Oumuamua touched 4 solar systems?
What they did was they have enough data on it to chart the parabolic path, right? And so what they basically did was they extended that parabola out, and they found 4 different star systems that they thought that it passed through between 1 and 7 million years ago. You know, obviously it takes time for Oumuamua to travel as well. And so they just identified 4 stars that were on the parabolic path.
Wow.
That one of them could be a home planet. And I'm not speaking home planet in the fact of aliens, but you know, sometimes an object can get jiggled loose for one reason or another. There are planets and stars that are not attached to a galaxy, that are just moving through space, and that's a whole nother science in itself.
Another question, if I might. How does the sun or the moon increase or decrease its masses? Is the moon decreasing its mass? Do you know?
Not appreciably. The sun is burning through hydrogen, and I don't have the stats, but it's a huge amount of hydrogen every second that it's burning through, and that's why at some point it's going to start burning helium, and when it does, that's when it starts shifting. In the end, when it burns through the lighter gases, and the gravity decreases, the shell starts. Half of its shell is going to come off in a planetary nebula. Before it does, it's going to turn into a red giant. And when it turns into a red giant, the boundaries of the sun will certainly swallow Earth, Mars, and maybe Jupiter. I mean, it's going to get big. That's still 5 million years from now. So if it is, it's very minute. You know, I mean, maybe the solar winds are blowing a little dust off it, but
Right.
Making it more dense. Yeah, I'm ignorant in that area for sure. You might be right.
So we do have a number of questions, so we're going to kind of... Did anyone in the back row have another question? All right. Hold on.
Oh, yeah.
Microphone.
The whole galaxy.
HOAG.
HOAG.
G as
So I was
in
trying to
George.
find it on my phone. I couldn't find it.
Try putting Hoag object, but Hoag should come right up. That's not a common. But Hoag object is. And the other thing you can do is Google Arthur Hoag. Arthur Hoag, the discoverer.
So I'm going to skip a few of the questions that I put in chat because I like to take notes. But one of the more interesting on the one you showed where the star was in the rings of the planet, shouldn't the star have cleaned up, have more mass and therefore cleaned up a good portion of the rings near it? Or is like the star orbiting the planet or the planet orbiting the
planet's
star?
orbiting the star, and I don't think that picture gave a good idea of the scale. The rings are blocking the star, but the rings aren't right in the star's face. There's still the rings are between the observer and the star, but the star is still quite a ways away. Or you're right, the rings would just fall. Actually, if they're close enough, they'd just fall into the star, right?
Possibly,
So
because
the artist's conception was trying to get the sun and the ring at the same time, and it probably looked a little closer than a real to-scale drawing would show.
cool. These are why we ask these questions. One of the next questions was, wouldn't a Dyson swarm, where it's like lots of little things with the thing, be more material efficient than a Dyson sphere or rings like you showed in the artist's conception?
It could. I mean, there may be design considerations. Since they don't exist yet, there may be some considerations that we don't know. Yeah, I mean, it could be panels. It could be bands. There are pictures of a Dyson sphere with like little panels and stuff. But the real point there was the astronomer Tabitha was saying that when it eclipses, there's still some wavelengths that get through. So it's most likely not a solid metal panel, whether it's a belt around the star or their panels. She's saying there's still some wavelengths getting through. So she thought it was more like a dust cloud effect, or like a comet or a debris field would a dusty debris field.
All right, another question from you guys.
What do you think will be the biggest thing the JWST teaches us about space?
Oh my goodness, that's a brain crusher of a question. The Hubble telescope set a lot of goals, and I think the JWST is just gonna give us a better idea maybe of the age of the universe. And when you look through a telescope, you're looking back in time. So when I say something's 7,000 light years away, what I'm also saying is that the light that we're seeing from that object is 7,000 years old. And we've seen objects that were as close to about 700 million years from what we think is the start of the universe. And so we can look at those really distant objects more accurately. When you're looking at something that old, what it's telling you is it's starting to tell you information about how galaxies are formed. And one of the surprises so far is that they found some really old galaxies that were much better developed than we thought an ancient galaxy would be. So the stuff JWST is going to show us is going to revolutionize our thinking in many areas of cosmology.
All right. First off, well, I know you're my mother, so Mom, can you please clarify the question you asked in chat, because I don't know what you tried to ask. Besides that, chat's gotten interesting into mythical creatures. You said Magnetar, and half magnet, half bull. I keep thinking Minotaur when he says it.
Okay.
and now we're on space vampires because they can be harmed by visible light.
Excellent. Thank you for that.
Regardless,
now I haven't answered that question in the future. Space vampires.
Regardless, the question after that was, do supernova usually explode evenly, like spherically-ish, or is it more irregular?
I'm still on that space vampire. I'm wondering if the space vampire stood in front of one of our telescope mirrors, if they'd see himself or not. But now they've really got. See, my mind is a scary place to be.
Yeah, someone said that's why you need refractors in space because there's no mirrors.
That's right. There you go.
Reflectors are mirror based, so.
You're never going to see the space vampire. I'm sorry. The question again?
Uh, Sorry. Do supernova usually explode evenly, like spherically-ish, or irregularly, like all sorts of
It's
wonkiness?
usually the remnants are irregular. We saw that Crab Nebula. It was anything but spherical. As a matter of fact, when we see something that's a perfect sphere, scientists stop and they say, "Wow, how did that get so perfect?" The explosions are all over the place, and there's also dust clouds sometimes restrict those relativistic jets, and so the core becomes a little disfigured, and there's all kinds of shapes out there. And supernovas, there are so many different types of supernovas now. Scientists need to rework the classification system, and that's a big battle in itself. But the old classification system just does not cover everything that we've discovered.
I believe you said the Chinese and Japanese, they saw the Crab Nebula. Is that correct?
They saw the supernova that created the Crab Nebula
Okay. Where did they see that happen? Do you know?
in
Like,
China and Japan.
In the year 1054.
1054. No, yeah, drawings and documentation that still exists to this day. I don't know what the medias they wrote it on, clay or what those documents were back then. But yeah, they observed it and they noted it. There's astronomy. The ancients had amazing ability in astronomical observation. Certainly, when a supernova goes off and you can see it in the daytime, that's like a big wow. But they didn't have as many distractions as us. And when you go out in the night, you go out and the stars were just amazing. I mean, you have to go to like New Mexico to get an idea of what the ancients saw. And, so they didn't have a TV, they didn't have air conditioning to bring them inside. So they would sit outside and they'd make observations and just wonder at just the glory that they're looking at.
All right. Another question is, where to go? Do you think we'll find other objects like Oumuamua that we might be able to visit with spacecraft like the one in that Arthur C. Clarke novel?
I do, yeah. I think that we will see more extraterrestrial comets or whatever that object will deem to be. We've already shown that we can put a probe on a comet when we know that it's coming, and so we, at some point we may be able to have some probes or vehicles that we can just set off as soon as we see it coming. Oumuamua was moving pretty fast, so that would be a
Intergalactic hit and run
tougher.
situation.
Yeah.
I am going to put a last call for questions out in our online chat. So if you have any pressing questions, do get them in. I do see a couple left that we'll get to. And I believe you had a question.
How does gravitational lensing works?
If you had a sheet that was stretched out and then put a medicine ball in the middle of that sheet, what would happen to that sheet? It would sag, right? So if I took a ping pong ball or a tennis ball and then I rolled it across the sheet, what would happen to that? It wouldn't go in a straight line, would it? Right? It would be, right? So think of that almost as the bending of space-time. And so if there's an object behind a very massive cluster of galaxies, the actual fabric of space has been bent. And so the light waves are not traveling in a straight line. They're going around that massive object. And in the process, they're becoming very distorted looking, but also magnified. I don't understand the physics behind it, but that's the best I can explain. it bends the very nature of space-time, and then light travels a path different than it would, and we get to see that from here because we now have the technology to look that deep into space.
All right. So my mom did clarify her question. She was referring to a Dyson sphere, and why choose a sphere? And Dan and actually had an because stars are basically spheres, and it makes sense.
Yeah, thanks.
There
Good
were-
question, though, Mom.
There were much more in depth, but I figured TLDR because I definitely did not understand the question. Was there another question out here? Bueller? I don't even get crickets this time because we're indoors. All right. So, I think the one last question here online. Where did it go? Oh, we answered that. Okay, perfect. Sometimes it gets weird when you go out of order because you're like, I don't understand. Maybe they explained further down. With that, I want to thank you all for joining us here. Thank you guys for bearing with us during our transfer into indoors. Despite how it looked, we have not practiced that before, so we're very happy that went off without a hitch.
Excellent.
Thank you, Walt, for giving another great talk. Like I said, do check us out on our website, uacnj.org, along with all our lovely socials. I'm going to go over to the sales desk museum area now to ask any questions you guys, or to be there for any questions you guys might have. And everyone, have a good night.
Yeah. Thank you.